Okay, so this is our first example problem for drawing shear force and bending moment diagrams for a frame. And we've talked about in class that the first thing we want to do is find the reactions. So let's do that. I think that'd be an easy place to start. I'm going to cheat a little bit and use this for my free body diagram. So at A, I'm going to assume that I have a reaction in the y direction and a reaction in the x direction. And then at D, which is a roller, I'm going to assume that I have a vertical force, I'll call it dy. And I'm going to find those just to get started. Also, to help me do this, I'm going to take this distributed load over here and turn it into a concentrated load that's equivalent. So it looks like it has a distributed load of 3 kips per foot over 12 feet. That's 36 kips. And that's going to be right in the middle, so that'll be about 6 feet from either end, whichever end you want. I also want to just quickly draw your attention to the fact that we've got this one concentrated force, and it's also right in the middle of this length, which looks like about 8 feet. So a pretty small little frame, 12 feet tall, 8 feet wide. Pretty big force on the side, actually, but that's not that important. So what do we do first? What would you guys do first to find these reactions? That's a great idea. So let's sum the moments about A. So I'll come over here and I'll assume right-hand rule for my sign convention, and we will sum the moments at A and make sure the structure is in equilibrium. So about A, the two applied forces create what kind of moment about A? Positive or negative? Negative. So I'll start with the first one. So I've got negative 36 kips for the force times 6 feet for the moment arm. This is also a negative moment, so negative 15 kips with a moment arm of 4. And then the thing I don't know right now, dy, is going to create positive moment and have a moment arm of 8. So what's dy equal to? Like 60 something? I don't know. What is it? 730. Anybody know? What'd you get, Mr. D? Oh, you didn't do it?
I got 34.5.
34.5?
That's what I got.
Okay, great. That seems reasonable. Rest of you guys getting that way? Okay, cool. So now we can find the reactions at A. I'll sum forces in the y direction. That's a pretty easy thing to do now that I have dy. Looking at my free body diagram, I have AY acting up. I assume dy also acted up. And then in the y direction, I only have one force, this 15 kip force, and it's acting down. So what should AY be? It looks like it's going to be negative, right? What do you guys get?
Negative 19.5 kip.
That seems reasonable. Anybody else get that?
Yes.
Cool. And then the last one that we'll do for the whole frame will be we'll sum forces in the x direction, make sure it's in equilibrium. In the x direction, we just have one reaction, AX, to the right, positive. And the other x force we have is the concentrated equivalent of 36. I think I might be able to solve for that one. AX is minus 36. So any questions about that? That's pretty straightforward from what we've been doing before. So the new thing now is that we're going to isolate each of these elements individually. So we would cut the structure up and separate it at B and separate it at C and find those internal forces. So from what we've talked about before, looking at the whole structure, what would be the easiest one to do first to find the internal moments at B or at C? Let me suggest, should I look at the section BC? That would be a bad choice, right? So what would be a good choice? Either CD or AB. Which one do you want to do first? It doesn't really matter. We're going to have to do both. You want to do the more challenging one first or the easier one first? Easy one first. So which one wins the easy one? AB or CD? CD. So let's do that. So let's look at section CD. So I'll draw the free body diagram for that section. The only thing we have acting on it is dy. We found dy. It was positive, so it's acting up. That's 34.5 kips. Now, at this section C, this is the first time I've looked at it, so I'm going to assume that CX goes this way, CY goes this way, and my moment, I know it's kind of squeezed in there, I'm sorry about that, but that's my sign conventions for everything at C. So I just need to find those three things. We have a free body. In 2D we have three equations of equilibrium and have three unknowns. Which one do you want to do first? Not really a big choice here. We always like to do the moment first, so I'll do that. So if I sum moments at C and make sure this free body is in equilibrium, what is the moment at C? Well, with my right-hand rule, this is a negative moment. And does anything else create moment about C? No. So that just simply says that the moment at C is 0. If I sum forces in the y direction, make sure I have equilibrium, what do we have? Well, Cy is up. This force, 34.5, is also up. So what's Cy equal to? Minus 34.5. Now remember, our ultimate goal is to draw the shear and bending moment diagrams. Are these y forces shear forces? No. They're actually axial forces. So would this element be in tension or compression? It's going to be in compression. If we drew an axial force diagram, then we'd have a negative value of 34.5 across the whole structure. Now I'll go ahead and finish this. Again, this is pretty trivial, but important. Trivial calculation. All we have is Cx, so Cx is 0. Now Cx in this element is a measure of the shear. So that means there's no shear force in this element. There's no bending moment in this element. So this CD leg of our frame, we don't have to worry about drawing the shear force and bending moment because there is none. Okay? Now what do we do? Well, we already talked about we're either going to do AB or BC or CD. We did CD, so let's do section AB. Just to make it a little cleaner, I'll draw a little line here, kind of separate it, and then I'll come and draw my free body diagram for AB. Now at A, I know AX, what is it? It was opposite that, so it's actually in this direction, 36 kips. AY we solved for of negative 19.5, so that's actually down. Did I get those in the right direction? Looks good. So now I'm going to come to B and I'm going to make my choices. So I'm going to assume that I've got a force in the X direction, a force, oops, almost wrote it as C, in the Y direction, and I'm going to assume my moment goes in that direction. These are not shear forces or bending moments yet, they're just forces and moment. Also, I'm going to transfer the fact that I have this concentrated equivalent force of 36 kips from the distributed load. So that should be enough information to solve for these moments and forces. So we're going to pick B as a good place to sum our moments because two of our unknowns go through there. So again, assuming my sign convention, right-hand rule, and summing moments at B, and then making sure we're in equilibrium. So this moment that I assumed here with my sign convention is a positive moment. About B, what's the moment due to the 36 kip force? Positive or negative? Positive. 36 kips with a 6-foot moment arm. What about this 19.5 force? Does it create moment about B? Does not. What about this 36 kip force here? Does. Positive or negative moment? Negative. And it has a moment arm of 12. So the moment at B looks to be positive and looks to be 218? Guessing. To what? 216. That's 216 kip feet. Now the positive just means that I've assumed the right direction here. Any questions about that? No? You guys fully recovered from spring break then? You're all in? Wow. Yes, you are. All right, so let's sum forces in the y direction. So I've got By acting up. I've got this 19.5 kip force acting down, and that's it. So By looks to be 19.5. Now again, do we care about the y force in this element? Not really, because it's an axial force, right? And we're not drawing axial forces. And also, the way it's drawn here, is this in compression or tension? It's in tension. Does that make sense that this leg would be in tension with this kind of force? Yeah, this big horizontal force is really trying to rotate the whole frame this way. So this element here is really holding it down. So in high wind loads, your foundation can hold your building down to keep it from flying away. One that is important to us is the x direction forces. So if I sum those, what do I have? I've got Bx to the right, so that's positive. I've got 36 also to the right, that's positive. And I've got this reaction force to the left, that's negative. So what's Bx equal to? Looks like it's 0. So Bx in this element is what? It's the shear force. So the shear force at B here is going to be 0. So any questions about that? So now I'm going to take this information and draw the shear force and bending moment diagrams. So I'm going to start by imagining this section AB rotated over 90 degrees. And I'm going to draw that. I think I can put it in right here. So I'm going to imagine this section AB here. And I'm going to have the distributed load, which is this value, of 3 kips per foot applied. This distance is 12 feet. And now I want to apply whatever the force in the x direction here is at A. And we just solved for that x direction force. What was it? It was negative 36, so it was going up. Right? What was the x force at B? Zero, right? Should I review? Bx, it was 0. What was the moment at B? 216 in that direction. So I'm going to apply that again here. 216 kip feet. And that's it. Because I don't care about the y forces, which have been the axial forces. So based on that, now you can really just stop thinking about the whole problem and then just focus on drawing the shear force and bending moment for this segment. So I'll assume my template. I will establish a positive x-axis and a positive shear, and all my values will be in kips. So looking at the diagram, what's the shear force at A where we're going to start? Looks like 36. Is that positive shear or negative shear? That's positive shear. I'm going to start with 36. Remember that the change in shear is the area under the load diagram. What is the total area under my load diagram? Base 12 times height 3, that's negative 36. So positive 36 minus 36 gives me 0. And that matches with the shear, which is 0. The change in shear with respect to x, or the slope, is the load. And you can look at our loading diagram and you can see that it's constant. So that's a constant slope, and it's negative. So here's my estimation of a constant negative slope. In fact, if I wanted to write it, it would be 1 to negative 3, and it would be this linear shape. Okay? Now we'll do the moment. So in a similar manner, I'll establish a positive x-axis, a positive moment axis, and I will put in the units of kip feet for my values. What is the moment at A? It is 0. What is the moment at B? It is, now drawn this way, is this a positive moment or a negative moment? Bending moment. It's a positive. So this is going to be a value of 216. Now we know that the change in moment is the area under the shear diagram. So what is the area under the shear diagram? Well, it's a triangle, so 1/2 base times height. And if you look at that, it's a positive area, and it's equal to 216. So 0 plus 216 is 216. So that's good. That matches. And then finally, the slope of the moment diagram is equal to the value of the shear. So what is the value of the shear right here? We go up. It's a pretty big positive number. So I'm going to draw a positive. And it decreases to 0. So here's my 0 slope. So I'll just sketch in kind of a quadratic curve that kind of matches that. So there's my moment diagram. Any questions about that? We're almost there. One more to go, right? So this was section AB. So let's draw section BC. So what I'll do is I'll come over here and I'll sketch the beam. Okay, right here in the middle is an applied force of 15 kips, and that's at 4 feet and 4 feet. Okay, let's put on there what we know. If you flip back and look at B, BY was, I assumed it was up on AB, so on BC it's going to be down, but we found BY to be positive, so that means that it's what? It's down, right? And that value was, what was it again? Lost track of it. BY was 19.5. What was the Y force at C? Well, let's check our CD beam. It was 34.5 negative. So it's down on this element, so it has to be up on the other one, 34.5. Okay? Now, what was the moment at C? Well, it was here. And we got a value of 216, and we assumed it was the right direction here. But of course, it's equal and opposite here. And what was the moment at C? 0. So I think we've transferred all the values. Check your notes, make sure I didn't make a mistake. Does that look good? Well, with that, then I'll go ahead and sketch in my template. So there's my left and right edge. I know something's going to happen here in the middle at 15, so I'll add that. And that's all I'll need to get started. So let's go ahead and draw this in. So I have a positive X, positive shear with units of kips. Now I intentionally drew this very short because I looked ahead and saw that my starting shear force is positive or negative? It's negative. So I'm going to start off at a negative value of 19.5. And then what's the shear force on the right-hand side? Positive or negative? That's also a negative shear force. Now the change in shear is the area in the load curve. What's the area in the load curve for the first 4 feet? 0. So there's no change. So this 19.5 value stays the same. And then of course the slope of the shear diagram is the load. Since the load is 0, the slope is 0. So there's my shear for the first 4 feet. You can see it's constant. Now as I go from the left side to the right side, passing through this 15 kip force, my shear changes that amount. Positive or negative? Negative. So 19.5 minus 15 is 34.5. Now the change in shear between these 2 points, well, for these things to match, it better be 0. And you look up here, and what's the area in the load curve? 0. That's great. And the slope is the load. The load is 0, so 0 slope. So we just have a nice, simple kind of step diagram for the shear force. So let's take that information and draw my moment diagram. So again, I'll assume positive X, positive moment. All my values will have the units of kip feet. What is the moment at the left-hand side? It is 216. Is that a positive bending moment or a negative bending moment? Positive. What's the bending moment over here at D? I'm sorry, C. It's 0, so I better hit 0. All right. So let's see how this is going to change. So according to my relationship, the change in moment is the area under the shear diagram. Well, here's an easy area to compute. Over the first 4 feet, what's the area under the shear diagram? It's this rectangular area, which is 4 times 19.5. What's that? And it's negative, so subtract that from 216, and what do you get? Sorry?
138.
138? What is the slope of the moment diagram? Well, it's the shear. So you look at the shear there, and the shear is constant and negative. So I'll draw a constant negative slope between those two. Now the change in moment from 4 to 8 feet is the area under that part of the shear diagram. What's that area? Hopefully it'll be 138. Negative 34.5 times 4. Is that 138?
Yes.
It is, so that brings me to 0. That's good. And then the slope of that diagram is the shear value. The shear value is constant and negative and a little bit bigger than the other one. So we'll see a change in the slope, and the slope will be steeper. There's my moment diagram. Now that we've completed the task, the question is, if you're designing a moment connection in this truss or this frame, what's the biggest moment that connection will have to withstand? It looks like it's 216 at B. Pretty cool, huh? If you're worried about your structure shearing here at this connection, what shear force do you have to design for at A? 36. So you have all the bits and pieces you need to take the loads, compute internal forces, and then take it to the design step. You don't have to worry about that this semester. Well, that's not completely true. Our second project, there'll be a design element that involves these. So any questions about that? Okay.